This is a continuation of a video that froze earlier, so make sure you watch part one before starting this one. I'm just continuing going over the points that we're going to impose. So in the original problem, we were given that y of 0 is equal to 0, y prime of 0 is equal to 3, and y double prime of 0 is equal to negative 8. Once we plug these in, so for example 0 and 0 for my t, that's going to eliminate some of these e terms and turn them into 1s. It'll eliminate this t term here, but the equations that we get look like this. Right, so this is our y prime, and our y double prime equations, and we can use those to solve for c1, c2, and c3. So I got 2, negative 1, and negative 2. For our general solution, we can leave these constants unsolved, but now that we know what they are, we can figure out our unique solution. So a unique solution is going to be this, where we plug those C1, C2, and C3 in. The next piece that I want to talk about, so this would be probably what I would ask you, right? If I gave you some third order initial value problem, then that's what I'd be asking for. I wanted to point out though, while I have this solution up, that we were able to solve for C1, C2, and C3, and we were able to, up here, we were able to factor what resulted from this. You know, for second order, if you're not able to factor this in your head, then you have to use that quadratic formula, x equals negative b plus or minus square root, so on. So I wanted to show you something. So this is the, if you have ax squared plus bx plus c is equal to 0, then you can solve for x this way. If you just have some constants here, so a, b, c, and d out in front of this x to the third term, so this would be like your third order differential equation, the equation gets a lot longer, so you're not going to be expected to memorize this. And my thought with this is that only certain constants out in front of higher order differential equations are going to result in something that you can do in your head. So I'll always be giving you something that you should be able to factor out by hand in this way without having to memorize that formula. So what I just showed you was called the cubic formula to find roots of cubic functions, and then it gets even worse as you go into fourth order and fifth order. They just become pages long to try and figure out what the roots are. So in a nutshell, what I mean is that something like this, where I just sort of, if I were to come up with an example off the top of my head and put some constants out in front here, there's a very low chance that it's going to work out nicely and be something that you can factor. I want to look at one more example, and that's this one. So I'll draw 4 hash marks here. Here I drew it, remember parentheses 4 means I'm looking at the fourth derivative of y. But here I've got the 4 hash marks minus y is equal to 0. If I assume y is equal to e to the lambda t, then I can rewrite this as lambda to the 4th minus 1 is equal to 0. And this is one that you can factor in your head. You have something squared minus something else squared. So in this case, lambda squared minus 1 squared. So we can split it up in this way. And then now we've got 2 quadratic formulas that we can split up. So I'll show you, split this one up to be lambda plus 1, lambda minus 1. And then this one, I sort of solved on the side here to say that lambda squared plus 1 is equal to 0 gives me, well, you've probably seen this in your examples, but lambda is going to be equal to plus or minus I there. So my 4 lambda values are going to be -1 for this one, 1 for this one, and plus or minus I are going to be my third and fourth values for lambda. We can have 4 solutions based on this. So e to the negative t, e to the t, and then for these I values here, you could write e to the it and e to the negative it, but I think it's much nicer to just write sine and cosine here. Again, just keep in mind that you've got an e to the alpha t term and sine of beta t to worry about for these. So if you had some real value in there, you'd want to think a little bit more about what your y3 and y4 were equal to. But you could solve it exactly like you would if this were just a second order differential equation. You could write out those solutions in terms of A and B. Okay, so I won't write it out here, but just so you know, you can, even with fourth order ones, you can still write it out as a linear combination: C1y1, C2y2, C3y3, and C4y4. Now, there's one other piece that I'd like you to know about higher order differential equations, other than being able to solve these ones if they're relatively easy to factor, and that's determining if a set of solutions is a fundamental set of solutions. So if you think about how we showed that a set of solutions was a fundamental set for second order differential equations, back when we did that, we found the Wronskian. And it turned out that if the Wronskian was not equal to 0, then the set of solutions was a fundamental set. And when the Wronskian was equal to 0, then it's not a fundamental set. You can also review the notes on Abel's theorem. That told us that basically we can choose any value for t as long as it's in the domain of the function, and then that will tell you whether or not it's going to be not equal to 0 or equal to 0. And that'll be true for the entire Wronskian, not just that point that you chose. In any event, for second order differential equations, we know that the Wronskian looked like the determinant of y1, y2, y1 prime, y2 prime. And then we found the determinant of that. That was our Wronskian. So you might be able to guess what the fourth order Wronskian would look like. And I won't write the general case because it's sort of a long process here, but second order looks like this. Fourth order, you just write out your 4 solutions, and then you make sure to go all the way down to the third derivative here. Like I said, I won't make you, I won't write down the general version of this because it's just, I think you can deduce the pattern from this. And another thing that I can promise, at least for all the final exam questions that I've seen, you do not have to do any determinants that are larger than 3x3s. So this 4x4 might be a little bit excessive. You might see maybe there's some sort of linear algebra trick that you can do where you have a row of zeros or something like that, or maybe a 1 and then the rest of the row is zeros. Excuse me. But in any event, those are the 2 things that I want you to know about higher order differential equations. Can you solve them? And given a set of solutions, can you show me that they're a fundamental set? All right, that's it for the video, and I will see you in the next one.